Determining a chemical formula from experimental data. Many chemical formulas were originally determined from experimental data where they took the compound and they decomposed it into its elements and found out it has this much carbon and that much sulfur. Or they took masses, they measured the masses that combined to form the total mass of the compound. So we can use that information. We can also use a percent composition to get an empirical formula. Empirical formulas, remember, are from experiment, and they give the smallest whole number ratio of elements. It's not actually the number of atoms necessarily in a unit or a molecule, and it's not the ratio of the masses. It's the particles. So I think the hardest thing about finding empirical formulas is just remembering what to do. So here's steps for those of you that like steps. You need to start with the masses of each element that are present in the sample. Sometimes they'll give you percentages instead of masses. What do? Well, make it easy on yourself and say, well, I'm going to assume that I have a 100-gram sample. And then if it's 69% oxygen, that means that there's 69 grams of oxygen. So if they give you percentages, just change the percent to gram and you're good to go. Then we need to convert the masses to moles for each of the elements so that we get number of moles. Then your book says to write a pseudo formula using the number of moles of each element as subscripts. I'm not a big fan of that, but if you want to do that, you go right ahead. Then you need to divide those subscripts or divide the number of moles by the smallest ones to get whole numbers. And if the result is within 0.1 of a whole number, you can round it to the whole number. But if it's like 3.2, you can't round that to 3. So it has to be within. And this is kind of a tricky area because there is error in the measurements because they were an experiment, right? And so it's not always going to come out perfect. And we're going to do an experiment like this in lab, and you're measuring things, and you're going to come out and you're like, I know the formula for this is such and such, but my numbers are showing me something else. Well, that's because there's some error in your numbers. So you divide to get, now you've got ratios. If those are whole numbers, great. If those are not whole numbers, you need to multiply all the subscripts in order to get a whole number. So this table can be helpful. These are using the idea of fractional subscripts. A fraction can also be represented as a decimal, right? 1/2 is 0.5. If we have something that ends in 0.5 and we multiply by 2, we're going to get a whole number. 1/3 is 0.33. If we multiply that by 3, we're going to get a whole number. So if you understand fractions, that's going to make sense to you. If you don't, then there's a trial and error method that works pretty well too. Multiply by 2. Is it within 0.1 of a whole number? Great. If not, try 3. Try 4. Try 5. You usually don't have to get past 5. Let's do an example, because all of that stuff just doesn't make much sense. A sample of a compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 22 grams of oxygen. Calculate the empirical formula of the compound. So the first thing is we need masses of all of the elements in the compound. So they gave that to us. So let's not write with the eraser. That's never a good idea. 165 grams of carbon and 27.8 grams of hydrogen and 220.2 grams of oxygen. First step. Remember what the second step was? Moles. We got the mass. We need to get this into moles because the formula gives us ratio of particles. This is masses. We have to get away from masses and get to particles. So I want to convert this to moles of carbon. Well, I do that using the molar mass of carbon. So grams of carbon, and so I'm going to have 165. See, I already did that one wrong. 165 divided by 12.01. 13.7386. In these problems, we're going to end up with whole numbers. And so carry extra significant figures. You really, really want to avoid rounding errors. So carry some extra sig figs. So that's moles of carbon. I'm not even going to keep track of them because they're all going to go away at the end anyway. So what's the point? Figuring out the mass of moles of hydrogen. 27.8 divided by 1.008. 27.5794 moles of hydrogen. Oxygen. Moles of oxygen divided by 16 grams. Some of these calculations can get tedious. There is a fair amount of tedium in science. There's just no way around it. But really, when you think about it, life can be tedious. Okay, did I do any of those wrong? Yay, yay for me. So we've got the moles. Then your book says to use these as subscripts and then figure out. That just doesn't make a lot of sense to me. If you like that, you go right ahead and do it. What I do is I've got all these lined up right now. I'm going to look and find the smallest one. These two are really close, but this is the smallest one. I'm going to divide them all by the smallest one. That way, all my ratios will be 1 or larger, and I won't, because we're trying to get rid of fractions and get to whole numbers. So I'm going to divide this by 13.7386. Well, that's easy. I don't even need a calculator for that. That's 1. 13.7386. 13.7386. We have to do the same thing to each of them or we're going to mess up the ratios. So 27.5794 divided by 13.7386. So that comes out to 2.007. Is that within 0.1 of a whole number? Yeah, it is. So we can round that to 2. And then this guy down here, you can already tell he's going to be close enough to 1. Yeah, 1.002. So also close enough to round. We got whole numbers. These whole numbers that we came up with, these are the subscripts for those elements. So carbon with a 1 that I'm not going to write because I'm a chemist, and hydrogen with a 2, and oxygen with a 1. And that is the empirical formula for that compound. Any questions? The hard thing is remembering the steps. Start with masses, convert to moles, and then we're looking for mole ratios, and we need to get whole numbers. Let's do another one. This is a percent composition. Ibuprofen, again, I like this because ibuprofen is what I say to my children when they have any medical problems. Mom, my ankles really hurt. Take some ibuprofen. Mom, I've got a really bad cold. Take some ibuprofen. And they almost don't even ask anymore. Should I take ibuprofen? They say, yes. So I like ibuprofen. This is the percent composition. And we're asked to find the empirical formula. So this is an example where they gave us percentages instead of masses, but that's okay. 75.69%. Well, if we say, I'm going to assume I have a 100-gram sample, how many grams of it is carbon? It's the same as the percentage. So just erase the percentage and write grams. Easier said than done. Grams. So for the hydrogen, 8.80 grams of hydrogen. And for the oxygen, 15.51 grams of oxygen. So we've got the grams. We convert to moles. So 1 mole of carbon, that's 12.01 grams of carbon. It's 6.30225 moles. Hydrogen, mole of hydrogen, over 1.008 grams. You can see how it's handy to have some of these molar masses memorized. And it's not that you actually set out to memorize them, it just kind of happens because you use them so much. And then 15.51 divided by 16. Moles of oxygen for 16 grams. And that gives us 0.969375. So moles. Oxygen, hydrogen, carbon. Anyone disagree? On a roll. What next? Divide by the smallest. We need ratios. So we're going to divide by the smallest. This one will end up being 1. And then we got this one, 0.969375. And you know, it might be tempting to say, oh, well, that looks like it's going to be 9. Well, just actually do it, because sometimes you can't quite tell. .005. Can we round that to 9? Yeah, we can. So let's look at this one. So this one comes out 6.5014. Can I round that one? Nope. So now what do? We're going to multiply all of them by 2. We can look at this and see 0.5. This is 6.5. If I multiply 6.5 by 2, I'm going to get 13. If you don't recognize that, 2 is the first place you start anyway. So you take that 6.5014 times 2, and I get 13.003. Beautiful. So times 2, 13.003. That rounds to 13. These other, bless you, were close to whole numbers, and so they're going to be fine. But you have to do the times 2. And this one will just be 2. If you multiply 1 by 2, you have to multiply all of them by the same number. So now we can see that we've got C13, H18, O2. Any questions? molecular formulas. The molecular formula will be some multiple of the empirical formula. Sometimes they're the same, but it could be multiplied by 2 or 3 or any number. So to find the molecular formula, we need to know the empirical formula and the molar mass of the compound. How would we get the molar mass of a compound? Well, that would come from something like mass spectrometry, where we can measure the mass of particles. So the idea is that the molecular formula is the empirical formula times some integer. So what we're going to do is we're going to take the molar mass, which in these problems has to be given to you because there's no way for you to calculate that. You take the molar mass, you divide it by the mass of the empirical formula, and you should get a nice whole number. Let's do an example. Compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What's the molecular formula? So we need to take the molar mass, 78.11 grams per mole, and we need to divide it by the mass of this formula. So the formula mass is 12.01 plus 1.008, which I think should be 13.018 grams per mole. So if I put that in there, again, don't round off a whole bunch of stuff. So 78.11 divided by 13.018 equals 6. What that tells me is that 6 of these units are within the whole formula. And so I'm going to multiply all the subscripts in the empirical formula by 6. So these were all 1s, and so I end up with C6H6. That's the molecular formula. Each molecule actually has 6 carbons and 6 hydrogens. But the lowest ratio is 1 to 1. A common technique for analyzing compounds, especially hydrocarbons and organic compounds, is to burn a known mass of the compound and weigh the products that are formed. The products that form when hydrocarbons burn are carbon dioxide and water. So all of the original carbon in the compound goes into carbon dioxide, and all the original hydrogen goes into H2O. Now, you can't measure directly the amount of oxygen originally in the compound, but you know the original mass. So if you subtract the carbon and the hydrogen, you can find the mass of oxygen. So this is what a setup, an experimental setup might look like. So you weigh the compound and you put it in a furnace. And there's oxygen blowing through this because oxygen is required for combustion. So this burns, and all the gases that come off from this burning are passed through these U tubes. They're shaped like U's. It has nothing to do with the website. So as it goes through here, we have a substance in here that will absorb the water. We weighed the tube before. As the carbon dioxide and the water pass through, all the water gets stuck in here. This tube will weigh more afterwards because of the water. And then it continues here and goes through a CO2 absorber, and we trap all the CO2. So we can get the mass of carbon dioxide produced, the mass of water produced. So these calculations can be very tedious. It's the same idea, it just involves a little more work. So upon combustion, a compound containing only carbon and hydrogen, this did not have any oxygen in it to start with, produced 1.6 grams of carbon dioxide and 0.819 grams of water. find the empirical formula. What do we need first to find an empirical formula? We need the masses of the elements, right? We don't have that yet. We have a mass of carbon dioxide, but all the carbon that was in there came from the compound. So we need to find the mass of carbon in 1.60 grams of carbon dioxide. And then we need to find the mass of hydrogen in 0.819 grams of water. And then we can start the whole process of finding the empirical formula. So 1.60 grams of carbon dioxide. Well, first we need to figure out how many moles of carbon dioxide is that. Well, I happen to know the molar mass of carbon dioxide. Moles of CO2. And then we want mass of carbon, right? So how many moles of carbon are in every mole of CO2? 1. So 1 mole of carbon to 1 mole of CO2. And then to find the grams, we would multiply by another fraction. Let's think ahead a minute. What are we going to do when we have the masses? We're going to convert them to moles. So here at this point, we've got moles. Maybe we should just quit here, and then we won't have to convert back to moles. So here we've got moles of carbon. 1.6 divided by 44.01 times 1. So there were 0.036355 moles of carbon in that compound. And then we need to find hydrogen. So we've got 0.819 grams of water. And we need to find first the moles of water. So we'll divide by the molar mass of water. And then we need to find moles of hydrogen. Well, what's the ratio, moles of hydrogen to moles of water? 2 to 1. 2 moles of hydrogen to 1 mole of oxygen. Water. 0.819 divided by 18.016 times 2. So this is 0.090919 moles of hydrogen. Okay, so at this point, we've kind of jumped into the middle of our list of steps, calculate the empirical formula. We've got moles of moles of elements. What do we do? Divide by the smallest. So we're going to divide both of these by this guy. So that comes out to be 1. And that comes out to be 2.5009. Now what do we do? Multiply by 2. Multiply that by 2, we get 2. We multiply 2.5 by 2, we're going to get 5. I'm multiplying by 2 because this is 2.5. I can't round that to a whole number. And so my formula then is going to be C2H5. Any questions? Individual steps, not hard. Remembering how to put them together could be challenging. I don't know about you, but I don't want to do another one. You with me on that? I'll talk about it for just a couple seconds. This question is a little more involved. They're giving you the mass of the original sample. they're giving you mass of carbon dioxide, mass of water. But this one has oxygen in it. So you do the same thing we did in the previous example to find the moles of carbon, moles of hydrogen. But then you have to figure out the moles of oxygen, and to do that you have to actually figure out masses of hydrogen, masses of carbon, subtract them from this. That gives you mass of oxygen, then you can convert that to moles, then you do the ratio, then you do the multiplying, and then you get your answer. Yeah. No way. I'm done.